Hello everyone, my name is Victor, and today I want to talk about halogenation of alkenes, which is a signature reaction of alkenes that has all components of a potential perfect disaster. This reaction has a rather complicated mechanism, and it is also stereospecific, so the stereochemistry is always going to be something to be very careful with. So in this video we're going to talk about everything you need to know about this reaction. Make yourself a cup of coffee, grab a notebook and a pen, and let's get started. So halogenation is a type of reaction where we are going to add some sort of a halide like chlorine, bromine, iodine, or even an interhalide where those are mixed up, and we're going to add that halogen across the double bond of an alkene, adding halogen to each of the carbons of what used to be alkene. So each carbon is going to get one of those alkenes. The important thing here, as I've mentioned a moment ago, is that the reaction is stereospecific, and in this particular case that is an anti-addition, which means that both of your halogens are going to end up on the opposite sides of the molecule, or rather I should say on opposite faces of the molecule, facing in different directions. Now, when it comes to the mechanism of this reaction, it is probably one of the weirdest one you have seen up to this date in your class. Let's start with some sort of generic alkene and the bromine molecule that are going to be reacting with each other. In this case, bromine is going to be our electrophile, or in other words, a molecule that is electron-loving, so it's going to be pulling electron density towards itself in this reaction. And my double bond, my alkene, is going to be the nucleophile, so it is going to be providing the electron density to make new bonds in this reaction. And here is something very interesting. When this reaction begins, we would expect a normal flow of the electron density from nucleophile to electrophile. So we will start with our pi bond, and those electrons go towards the bromine. Bromine will release electrons towards the other bromine, and everything seems to be perfectly normal in this case. However, at the same time, the original atom of bromine that's receiving that electron density is going to attack my alkene back, forming another bond. So as a result of this transformation, as a result of this electron flow, we are going to get the following intermediates. We are going to have a three-membered ring with the bromine that is now going to be double bonded. It's going to be bonded to one carbon and to another carbon at the same time, and we're also going to form a Br-. I know it feels a little bit weird to have a plus charge on a halogen like bromine, but that's the way this mechanism works, so we're going to roll with that. Now, the important thing here is to recognize where exactly all of our electrons are. So let's make a very careful analysis of everything that's going on there. The electrons of the double bond, I will highlight those in green. Those electrons are now making a bond between one of the carbons and the bromine. The electrons that used to be between my bromines are now one of the electron pairs on my Br-, and the electrons that I had on my bromine that was attacking my double bond, those electrons are now on this bond connecting bromine to another carbon atom. We are also going to be commonly referring to this three-membered intermediate as a halonium ion, bromonium ion in this particular case. Now, the next step in this mechanism is going to be the nucleophilic attack, during which the Br- is going to be attacking one of our carbons, and it's going to be forming a new carbon-bromine bond with our second bromine. So let's say my Br- is attacking my top carbon. That means that the green electrons now have to go back to my Br+, and that's going to give me my final product where each carbon is connected to its own bromine atom. And for as long as we are dealing with simple halogenations like that, our reaction is always going to be just a simple two-step reaction, starting with the electrophilic attack, followed by the nucleophilic attack. Looks easy enough, right? Well, not so fast. Let's look at the actual example. In this reaction, I am trying to react 1-methyl cyclohexene with the bromine molecule. So step number 1 during our electrophilic attack is going to be the electrons of double bond reach onto bromine, the bond between my bromines going to break, and my initial bromine atom is going to back attack one of my carbons to make the second carbon-bromine bond. Now, since in this case the attack by bromine can happen from the front face of the molecule or the back face of the molecule, I'm going to end up with two different intermediates. In the first case, where let's say my bromine is attacking from the front face, my intermediate is going to look like this. And in the second case, when my bromine is attacking from the opposite side of the molecule, I'm going to end up with a molecule with the bromine looking away from me. And because in the first case, let's call that intermediate A, so in the intermediate A, my bromine is looking at me, it forces the methyl group, the CH3 over here, to look away from me. In the second case, let's call that intermediate B, I have the opposite situation. Bromine is looking away from me, which forces my methyl group, CH3 group, to look at me. So the next step is going to be the nucleophilic attack. And here we are going to see something very interesting. When my Br- attacks to open my halonium ion, it is predominantly going to be attacking from the more substituted side of that ion. So here I have atoms number 1 and atom number 2. So atom number 1 has more groups on it than atom number 2, which means that my Br- is going to be attacking that carbon. So Br- comes in, attacks right over here, the electrons go back onto the bromine, and that going to give me the final product that now is going to look like this. The important thing here to notice is that the carbon number 1, where my attack has happened, has undergone the stereochemical inversion. So since bromine has to attack from the opposite side where the original Br+ is sitting, it is going to push everything around and basically kind of flip that carbon around. So my methyl group that I had over here looking away from me now is going to be looking at me, while the Br is looking away from me again. Now, the original bromine that I already had on my molecule, I will highlight that one in blue, well, that bromine is still looking at me, because the only thing that we did, we broke the bond between that bromine and carbon number 1, but we did not touch the bond between bromine and carbon number 2, which means that it's still going to be looking at us. A very similar situation is going to happen with the intermediate B. There, when we are going to be doing our attack with the Br-, we are again going to be attacking the more substituted carbon, which again going to be carbon number 1. And in this case, when my Br- attacks, the electrons go back onto the Br+, and we are going to have the final product looking like this, where my new bromine is looking at me, my old bromine, I will also highlight that in blue, like in the other case, is looking away from me, and the methyl group, now that methyl group is pushed away from us, so it's looking away from us. In this particular case, the relationship between these two molecules is going to be enantiomers. These two are non-superimposable mirror images, and you can confirm that by assigning your R and S stereo descriptors if you like. So the important thing to remember about this reaction is first of all that you are going to have the anti-addition, meaning that both of your halogens are going to look in the opposite directions from each other. And another thing to remember here is that we are always opening our halonium ion from the more substituted side. We're always going to be attacking the more substituted carbon of the halonium ion with our nucleophile. I'm going to talk about why this type of intermediate typically undergoes opening from the more substituted side in another video. For now, just remember that whenever you see something of this sort, where you have a three-membered ring with an X with a plus, where X can be halogen, oxygen, or some other atom, you're going to see also reactions with mercury that work in a similar way. You should always attack those type of intermediates at the more substituted carbon, so at the carbon that contains more different groups. And why does that matter? Well, in a simple halogenation, it really doesn't. However, in reactions with interhalogens, where I have mixed halogens, or reactions when we have alternative nucleophiles, not just X- but something else, then it does make a huge difference. Let me illustrate it with an example. Here I have reaction with iodine chloride, and the very first question that I have here is what exactly is going to be my electrophile? Is it going to be the iodine or is it going to be chlorine? So if we look at the periodic table, we can see that iodine is lower than chlorine in the periodic table, which means that iodine has a lower electronegativity than chlorine. So chlorine is going to be pulling electron density towards itself like that, giving a delta plus or partial positive charge onto the iodine and making itself partially negatively charged. That means that in this particular pair, iodine is actually fairly electrophilic. It is a halogen to begin with, and now somebody else, some other halogen, pulls the electron density out of it, so that's going to make our iodine fairly electrophilic. So the first step in this reaction, like in any other halogenation, is going to be where the double bond attacks the iodine, the electrons between iodine and chlorine go to chlorine, and my iodine is going to attack one of our carbons of the alkene back, giving me the following intermediates. Here, since iodine was my electrophile, it is going to be the iodine that is connected to both of my carbons, and the nucleophile here is going to be my Cl-. Now, I've mentioned a moment ago that the attack by the nucleophile in these cases happens from the more substituted side, so we're going to be attacking a more substituted carbon. Here I have my carbon, let's call them A and B. So my carbon A has 2 alkyl groups on that, my carbon B only has 1 alkyl group on that, which means that carbon A is actually more substituted, which means the attack by chlorine is going to happen from that direction. It's going to happen on the atom A. So I will show that chlorine is attacking right over here, and the electrons go back to iodine. So once we open this halonium ion, we are going to end up with a final product like that. And the other possibility, the other theoretical possibility, where I would have my iodine on the more substituted carbon and chlorine on the less substituted carbon like that, that is not generally observed in any appreciable amount. This regioselectivity is very important, and I can guarantee that this is something that is definitely going to be on the test, and your instructor is definitely going to be asking you questions about this specific regioselectivity of this reaction. Now, if we go back to the stereochemistry of this reaction, we remember that this reaction is an anti-addition, which means that both chlorine and iodine should be looking in different directions from each other, which means that one of my products will look like this, where I have the chlorine looking at me and iodine looking away, and the other product is going to look like this, where the chlorine is looking away and iodine is looking at me. Now here, while it is not incorrect to draw something like that, it is important to note that the atom with the chlorine here, that is not a chiral atom. So technically we do not need to show any stereochemistry at the chlorine atom because, well, it doesn't really give us any additional information. So you can just draw a plain line for your chlorine and that will be perfectly fine. And in this particular case, again, the stereochemical relationship between my two products is going to be enantiomers. Let's look at this example over here. In this reaction, I have my iodine reacting with an alkene, so the first step, like in the previous cases, would be the electrophilic attack of the iodine on my alkene. So I'm going to redraw my starting materials like that, and I will show that the alkene attacking the iodine, the bond between the iodines break, and my top iodine is attacking one of the carbons back, forming the iodonium ion that will look like this if iodine attacks from the front face of the molecule, or like this if iodine attacks from the back face of our molecule. And of course we also have the I- that is going to be floating around as our nucleophile. So the next step is going to be my nucleophilic attack, where I'm opening my halonium ion, and in this case iodide again going to attack the more substituted carbon of my halonium ion, which is the left carbon in this particular case, opening my halonium ion like this, or in the other molecule and another enantiomer, it's going to be like that, which is going to give me the following two products. And in this case, the relationship between our products is going to again be enantiomers, like that. So do we always get enantiomers? No, we actually do not. Like in any other reaction, avoid making blanket statements and always analyze what you have in front of you. For instance, here is a classic example of cis and trans stilbene being brominated. In the first case, I'm going to make a product which looks like this, where I still have my phenyl groups and one bromine is looking at me while another bromine is looking away from me. That is going to be a mesy compound. So that is an achiral molecule. While in the case of the cis stilbene being brominated, I'm going to have a product that looks like this, where one bromine is again looking at me and another one is looking away from me. But that is actually a chiral molecule. So I'm going to get this one, and I'm also going to get its enantiomer, which is going to look like this. So I have Br over here, and I have another Br on the left side like that. So these two are in fact enantiomers. And you might ask me, are there any other tricks like that? Well, of course, you can make diastereomers in this reaction if, let's say, your starting material has chiral atoms to begin with. For instance, let's look at this reaction. If I were to draw my products real quick here, then I'm going to get one molecule where the chlorines are going to look one away from me, another one is going to look at me, and the other possible product here is going to be, again, the molecule where one chlorine is looking at me and another chlorine is looking away from me. In this particular case, the relationship between these two molecules is going to be diastereomers. And the important thing here is that the stereochemistry at the carbon with the methyl group, well, that one did not change. So you gotta be very careful paying attention to those things that had stereochemistry to begin with, and you may or may not change them during your reaction. So in this case, you ended up with two molecules that are neither mirror images nor they are superimposable in space. So by definition, they are diastereomers. So as you can see, this reaction can give you enantiomers, it can give you diastereomers, or it can give you a completely achiral molecule, or even a meso molecule as well. So be extremely careful with the stereochemistry here, because it is really easy to walk into a trap. And talking of traps, here is a very good question. This seemingly straightforward multiple choice question asks you to find the correct product for this reaction. What could be easier, right? And you're probably looking at me and you are thinking like, Victor, are you barking mad? Nothing here is correct. None of our halogens are anti to each other, they are not trans to each other. How any of that can be correct? And that is because, well, molecules don't care how you draw them. They just, well, exist, which means that you have to pay very close attention to how exactly your molecules are drawn, and if in the answer options you have a different confirmation of a correct product. So let's forget about our answers for the moment here and look at how the correct answer for this question would look like to begin with. So here, if I do the halogenation, I would end up with a product that looks like this. So I will have my bromines either looking one at me, one away from me like this, or another possibility, the enantiomer of the molecule above is going to look like this, where I have my bromine looking away from me and the other one is going to be looking at me like this. So it means that I need to think about all possible conformations of these two molecules and to see which of those conformations might be in front of me on the right side. So the first thing that jumps at me right away is the molecule D, where I have both of my halogens on the same carbon. And I know that the halogenation reaction gives me a product with the halogens on the adjacent carbons, not on the same carbon, which means that that cannot be my final product here, cannot be the correct product, so I will X that one right away. The rest of my molecules have halides on the adjacent carbons, so they can potentially be a possibility. So I'm going to pay a very close attention to how exactly my carbon skeleton looks like, and I will see that the way I drew my products, I have my typical zigzagging of the skeleton, and I have the same zigzagging in the first option as well. However, in that first option, my bromines, they are looking in the same direction, they assist to each other, which means that cannot be the correct answer either. So now I have B and C, where my overall skeleton is a little bit twisted in space, so it is going to be a little bit more challenging to see right away which one might be the final product for that one. So maybe, if I don't want to draw Newman projections or anything of that sort, I can assign the RNS stereodescriptors. So the RNS stereodescriptor over here, that is going to be the R, and this one is going to be the S stereodescriptor. In the bottom molecule, it's going to be the opposite. It's going to be S here, and it's going to be R over here. So I'm going to look for RS or SR stereodescriptors for my products. If I look at the molecule B, this one over here, well, that one is the S stereodescriptor, so looks promising. If I pay attention to the other one, to the second bromine here, then that one is going to have my lowest priority looking at me over there like that. So that one is going to be also S stereodescriptor. So SS does not fit any of our two possibilities that I have for the actual product. So that cannot be the correct answer either, which means that I end up with the option C as the correct answer. But let's double check that one just to make sure. So this carbon over here, that one has the R stereo configuration, and this one over here, my lowest priority hydrogen is going to be looking away from me, so that one is the S stereo descriptor, which is exactly what I have on top for my correct answer the way they should be. So be extremely careful with reactions like that, because your instructor can easily put trick like that on the test, and I have seen that happening multiple times. So as you can see, the halogenation of alkenes, this reaction can be full of tricks, and you should always treat this reaction with the utmost respect, otherwise you will walk right into a trap that your instructor put on the exam. Thank you for watching this video. I want to especially thank all the organicchemistrytutor.com members and my generous donors. I upload new videos every single day, and this is only possible due to your help and encouragement. If you learned something new today, please give this video a like and leave a comment below so YouTube shows it to more people. In the meantime, watch this video next, and I will see you tomorrow.